In the second part, we're going to look at the definition now of linear independence and dependence. To do that, I'm going to let V1, V2 through Vp be a set of p vectors in Rm. So they're all living in the same dimensional space, and I have p vectors here that I'm interested in understanding how they may be dependent or independent of each other. We're going to say that that set of vectors is linearly independent, so that's the concept that we're defining, if some condition is met. Motivated by what we saw a moment ago, we're going to look at the homogeneous equation. On the left-hand side, I'm going to take a linear combination of those p vectors, and I'm going to ask, is it possible to get 0 from that linear combination? And if the only way to get 0 is to put 0 in front for all the weights, then we're going to say that these vectors are linearly independent of each other. So the condition that needs to be satisfied here is that this equation has no non-trivial solutions. There is no interesting way of linearly combining these vectors to get 0. You can only put 0 in front of all those weights to get 0. That would be a situation where the vectors are linearly independent. On the other hand, if that equation has non-trivial solutions, we're going to say that that set of p vectors is linearly dependent. There must be some numbers, not all of which are 0, that I can put in front to establish an interesting linear combination that gives me 0, and therefore some interesting dependencies among those vectors. At this point, I would encourage you to pause the video and review the 3 previous motivating examples from the last portion, and see if you can come to your own conclusions about how the definition will apply to those 3 examples. Are they linearly independent or dependent vectors in each case? And then we'll summarize that in a moment. Okay, so let's return to our first motivating example. We had u was 2, 1. We had v was v2. We saw that we could double one of the vectors to get the second one, and we expressed it as a homogeneous expression. 2 times u minus v is equal to 0. According to the definition, the homogeneous equation relating those 2 vectors together must have some non-trivial solutions. In fact, if I could take 2 and minus 1, I will get an example of such a non-trivial solution. There are many other non-trivial solutions, infinitely many in fact, but just the fact that there is one non-trivial solution is enough to come to the conclusion that my 2 vectors form a set of linearly dependent vectors. Let's look at our second motivating example. I now have the vector w, which is 2, 0. We observed that there was no way to scale one of them to get the other one, but we reinterpret that in terms of the homogeneous equation, and we convinced ourselves that that homogeneous equation has no non-trivial solutions. There is no way to put anything other than 0 in front of these vectors to get 0. If at least one of these numbers was 0, you would be able to solve for one of the vectors, and we would have observed that one was parallel to the other one. Because it has no non-trivial solutions, the set containing these 2 vectors u and w is a linearly independent set. Finally, I'm going to take the 3 vectors v1, v2, and v3. v3 is the vector 6, 2, v2 is the vector 2, 0, and v1 is the vector 2, 1. And we observed in the motivating examples that twice v1 plus v2 minus v3 is equal to 0. So the homogeneous equation associated with those 3 vectors has non-trivial solutions, and therefore my 3 vectors form a set of linearly dependent vectors. You can see here an example of how the vectors are dependent on each other.